All right, we're going to look at a fairly simple problem. This is 5.14, so it's chapter 5. We're going to look at this problem here. It says we have an overhanging beam supported by a pin at A and a 2-force strut BC. Okay? Determine the horizontal and vertical components at A, the reaction at A, and the reaction at B on the beam. Okay, so remember essentially, guys, in chapter 5, we're not only looking at trying to calculate resultant forces, resultant applied forces and moments, we are also trying to determine reaction forces. Okay, and when we try to determine these unknown forces, we need to know when we are calculating, or when you're drawing our free body diagram, we need to know what kind of reaction forces do I replace these various reaction elements with. Okay, so I'm just going to quickly see if I can find this very important table here. So this table is very, very important. Table 5.1. It shows us all the types of elements we can get, connectors, and then how do we replace these ones with forces when we are drawing our free body diagram. Okay, so you can see that there's a rocker. What do I do if I draw the free body diagram? I replace it by the force. That's normal. What about a smooth contacting surface? I replace it by a force, a normal force. Roller and a pin. Okay, so some very important ones which you need to take note of. Well, they're all important, but a roller, very important. How do I replace this kind of reaction with a reactive force, like we just discussed? Some more important ones, a pin. We want to replace this connection with a reaction force. We can replace it with an X and a Y force reaction. What about a member fixed, connected to a collar on a smooth rod? So essentially, the question is, how do we know which forces to replace this connector with, which forces to apply there? The simple thing is, what is this connector doing in terms of resistance? Is it stopping translation? If it is stopping translation, then we have to apply a force. Meaning, if I'm applying a force here, and I'm trying to draw in some reactive forces, is this connection stopping this object from moving? Well, then we have to put in a reaction force. If I try to apply a moment, does this connector try to react against that moment? Then, if it's true, then I need to put in a moment. What about a fixed support? This reaction, will it stop translation? Yes. So, well, should I rather say, is there the potential for this type of connection, this type of support, to resist forces in the X and Y? The answer is yes. If I apply a force in the X, then there's going to be a reaction force opposing it. If I apply a force in the Y, there's going to be a reaction force. And if I apply a moment, then there's going to be a reaction moment, okay? So, for example, a pin, it's not going to stop any moment. If I apply a moment about this point O, this pin is not going to react against that moment. There's not going to be a reaction moment, okay? So please study this table 5.1 and really understand how to put in the appropriate forces. Okay, now we need to just go back to this problem. Sorry, this is all over the place. You see, we've got two beams. We've got this beam, and then we've got this strut, okay? So we need to determine what are the reaction forces at A and what is this reaction at B. Okay, so let me quickly draw this guy. Okay, and then we've got this strut over here. Okay? Don't worry about being so pretty. Okay? So we've got this 600 here. We've got an 800 there. We've got a couple moment, these are Newton, got a couple moment of 900 Newton meter. And we've got, this is point A, and this is point B. Okay, so how do we solve this problem? Well, let's draw a free body diagram of this beam at the top. Okay, we've got our 600 here, we've got our 800 here, we've got a 900 Newton meter here, and this is 1 meter. This length here, and then we've got this FB, okay? That's the force of the strut onto this horizontal beam, okay? And then that distance there is 2 meters. You can just look at it in your textbook, okay? This is the 13th edition. That's also 1 meter. Now, what do we replace this? There's a pin here. This is not a fixed support. This is a pin support, okay? How do we replace this with forces? Right? Well, there we can say AY and AX. Okay? So this is very important to notice that when we've got a pin support, the pin support can only resist translational forces, right? Can only resist in the X and in the Y. There's no moment resistance for a pin support. So that's why we do not put in the moment reaction force here. Okay? So I think this is pretty good. The other very important thing which I wanted to quickly mention, that's why I chose this, is something called, this is just an aside, but maybe not such an aside. It's a two-force member. Two-force member. Okay? So a two-force member, if you look here, a two-force member looks like this. This is section 5.4. A two-force member, the basic idea is that it's a member and it's got two forces acting on it, okay? And if this member is in equilibrium, guys, please take note of this. If the member is in equilibrium, if it is in equilibrium, then it has to follow this rule. The forces must be equal, opposite, and along the same line of action. If the member is in equilibrium, the forces must be equal, opposite, and along the same line of action. Why? Because if it is in equilibrium, the forces must cancel out and the moments must, the sum of the forces must be 0 and the sum of the moments must be 0. Okay? So if I've got a two-force member here, and this member is in equilibrium, then the sum of the forces must be 0 and the sum of the moments must be 0, right? If this is in equilibrium. So if I've got a force here and I've got a force there, how are we going to satisfy this first criteria? Only if they're along the same line of action, okay? And how are we going to satisfy this criteria? Only if our moment arm between these two is 0. So, for a two-force member, if it is in equilibrium, then this is what is happening. The forces are equal, opposite, and along the same line of action. Okay? I hope that's very clear. So now, when we come to this strut here, this is a two-force member. Okay? So that is why, when we draw the free body diagram of this top beam, we know that because this is a two-force member and it's in equilibrium, right? It's not translating anywhere and it's not rotating, then we know it has to follow this rule. The forces must be equal, opposite, and along the same line of action. So the line of action is just simply going to be from that point to that point, there's my line of action, right? So that's where the force is acting. It's acting along that line of action. And yeah, that's it at point B. Okay, so that's your 30-second teaching of a two-force member. Okay, I think that's good enough. Now that we've got this, now we need to just set up our equations of equilibrium and solve for the unknowns. Okay, so sum of the forces in the x equals 0. So what are our forces in the x direction? I've got AX, and I've got this component of FB, right? By the way, I just want to tell you that it doesn't matter what direction you put your forces in, right? Because when you calculate when you're trying to solve using your equations of equilibrium, the direction kind of comes out in the wash, so to speak, right? If we've chosen it to be this direction and we get a positive answer for AX, it means we've chosen the correct direction. If we choose this direction and we get a negative value for AX, it means that it's just going in the opposite direction, okay? So I hope that's okay. So we're trying to get sum of the forces in the X equal to 0. And the only forces in the X direction are our reaction force, because it's a pin here, and the horizontal force of FB. Now, I don't have time to go through this because I don't want to make this video too long. But this angle I calculated to be 40,96 degrees, okay? You can go and work it out because this is 1.5 and that's 2. So you've got a right angle triangle. You can go calculate this angle, okay? I'm not going to go into that in detail, all right? Okay, so we've got the sum of the forces. So we've got AX plus FB cos of 40,96 equals 0. We don't know what is FB. We don't know what is AX. So sum of the forces in the y equals 0. What are the forces acting in the y direction? We've got AY, we've got minus 600, we've got minus 800, and we've got this vertical component of FB. So we've got 1, 2, 3, 4 forces. So we've got AY. Remember again, I've just chosen AY to be upwards, but you can choose it downward. The simple thing is, if you solve for it and it's a negative, then your arrow is in the wrong direction. Okay? So AY minus 600 minus 800 plus FB sine of 40,96 equals 0. Okay? Then, the last thing we can check, because we don't know what is AY and we don't know what is FB, but even, yeah, so we've actually got three unknowns and two equations here. So we need another equation, sum of the moments about A. Let's choose to take moments about A, all right? Because that will cancel out the AX and the AY reaction forces, okay? So the sum of the moments about A, minus 600 times 1, minus 800 times 4, minus 900, okay, sorry, okay. It's this 600 times 1, that's my clockwise. And I've got 800, and then the moment arm is 4. Then I've got 900, which is also clockwise. And then I've got this FB, the vertical component of FB, times 2. And that's a positive, right? So plus FB sine 40,96 times the moment arm 2 equals 0. All right. So that's the straightforward idea. I'm not going to go into solving everything. AX is minus 3134, okay, Newton. Essentially what that means is when I solve for AX, I hope I'm right now, okay, I chose my AX to be this way and I ended up getting minus, so that means my AX is actually acting in the other direction, okay. AY was minus 950 Newton, which means that it's acting down actually. My AX was actually acting to the other side, and my FB was 3917,2 Newton. Okay? So yeah, I hope you learned something in this short video. Cheers, guys.